Hi, this video is about polarity and intermolecular forces or forces of attraction. So just to review electronegativity, remember that electronegativity is the ability of an atom to pull electrons that are in a bond towards itself, and the electronegativity values are on your periodic table. So remember, they go up to 4.0. So we've talked about ionic and covalent bonds. Now we're going to differentiate two different types of covalent bonds. Nonpolar covalent is when these are kind of silly, but if you think of the electrons as the blanket, if you're sharing the blanket or the electrons equally, then we consider that a nonpolar covalent bond. If they're sharing but not sharing entirely equally, the atom with the higher electronegativity will pull the electrons towards itself more. Then we have what we call a polar covalent bond. And then ionic is when we have that transfer of the electrons. So we are going to be using these values for determining what type of bond we have. So when we have a bond between two elements, we'll subtract their electronegativities, and then if they fall in these different ranges, then we consider them nonpolar covalent, polar covalent, or ionic. It's not really a definite all of a sudden it turns into ionic. It's actually just kind of as you're going this direction, the bonds become more ionic. But we will use these numbers as cutoffs. So what type of bond occurs here between like boron? And what I would do is I'm looking at my periodic table, and I can see boron has an electronegativity of 2.0 and chlorine is 3.0. So the difference is 1.0, and that falls in that 0.5 to 2.0 range, which means this is a polar covalent bond. So this, let me see, like any one of these bonds is polar covalent. So let's keep doing a couple more. So this bond now between carbon and oxygen, again, I would just look at the electronegativity of carbon, which is 2.5. Oxygen is 3.5, another one that's 1.0. So this is also polar covalent. And then lastly, we've got carbon, which is 2.5, and chlorine, which is 3.0. And we get a difference of 0.5. So this is polar covalent, but not as polar covalent. So, and for some reason, I didn't give you any examples of nonpolar covalent. I think one example would be, here we go. This is methane. So carbon is 2.5, hydrogen is 2.1. So the difference of those is 0.4. So those would be nonpolar covalent bonds. So we would say that they're sharing those electrons about equal. So we do use Greek letter delta to represent partial negative and partial positive charges. So for example, so they're not really, we're talking about covalent right now, so they're not ions, but they become partially, not completely, cations and anions. So for example, here we have hydrogen, which is an electronegativity of 2.1, and fluorine is 4.0. So this is would be a difference of 1.9, so it's very polar covalent. So what we would do is the fluorine is the one that's going to pull the electrons closer to itself, so it's going to become partially negative and pull those electrons away from the hydrogen, which makes it partially positive. We also can use what we call a dipole arrow and draw an arrow pointing to the one with the higher electronegativity. And then we put a little tail on it that kind of represents that positiveness that's left behind. So covalent bonds, this would be now after you've done the PhET on molecular polarity. We can look at, when we do the PhET, we're going to see that there's polar bonds, but then also the molecule itself can be polar. So that means overall there's a negative end of the molecule and there's a positive end on the molecule. So this is an example. This gold arrow is showing that the molecule is polar. It's partially negative on the fluorine end and partially positive on the hydrogen end. So when we do the PhET, you're going to discover that some shapes are always polar because they're not symmetrical, which are the trig pyramidal and then also bent. So those shapes are always going to be polar because there's no way for their polar bonds to cancel themselves out. And they also have lone pairs of electrons, which lead to them being partially negative on the side with those lone pairs. And then there's shapes that are nonpolar. If you have a trig planar or a tetrahedron, as long as all of the atoms around it are the same, then they essentially cancel out and the molecule is nonpolar. But if you all of a sudden have a different, any one of these is different, like let's say we have a fluorine, a fluorine, a fluorine, and then a hydrogen, this is going to be polar. Linear, you do have to just kind of think, like if you have a linear shape here, this is going to be nonpolar because they're identical. But if you have like carbon dioxide, this is nonpolar also because the symmetry of the molecule, if you have a bond dipole, like if the oxygens are each pulling on those electrons, essentially it cancels out. But if you have a linear like this one, now the nitrogen is going to pull harder on the electrons and the hydrogen, and then between these electrons and the carbon's going to pull harder on these electrons. So this is non-symmetrical, so this would be a polar molecule. So now if we go back to our notes, we can, kind of write in that last column. So tetrahedrons are nonpolar if the atoms around the central atom are the same. So this one here is going to be polar because they're not all the same. Trig pyramidal, remember they're always polar. So are bent. And then linear, they're nonpolar if they're identical atoms. So in this case, this one's polar. So there's sometimes polar, I guess I would put here. And they're nonpolar if you have identical atoms, like if you had a fluorine and a fluorine, this would be nonpolar. So then if we keep going, trig planar, remember that rule is the same as our tetrahedral rule. So I'm going to try to copy this and I'll explain it again. paste. So tetrahedral and trig planar, as long as the atoms going around the central atom are the same, then it's nonpolar. So this example is nonpolar molecule. If this was one of these was like a hydrogen, then it would have been polar. Bent, this is another bent, so always polar. And then these linears are kind of similar to the previous linear. They're sometimes polar. This example is nonpolar molecule because they're identical. And then when we get down to the sp hybridization, this one would be polar, and so would this one. But if I had carbon dioxide, it would be nonpolar. So it's really, you have to look at when it's a 3-atom linear, it's really kind of that same rule as the trig planar and the tetrahedrons. If the outside atoms are the same, then it's going to be nonpolar. If they're not the same, then it's polar. So now we're going to talk more about intermolecular forces. So an intermolecular force is the attraction between molecules. So for example, like here you have, that's a real bond. That's what we call an intramolecular. These should have their dots, but this is relatively strong. But this attraction now between this molecule and the nearby molecule, this is what we call an intermolecular force. These are weaker, but they still are important. So they vary in strength. And we're going to learn about the different types of these. So there are 3 types of intermolecular forces. We do call them IMFs. First one is dispersion forces, second is dipole-dipole, and the third one is hydrogen bonds. So dispersion forces are when every molecule has this. So at any given point, it can, just by chance, there could be more electrons on one of the ends than the other. And that causes that molecule to become partially negative on that end. And then the other end where the electrons are not as much becomes partially positive. So a nearby molecule can be doing the same thing. And then the IMF, the attraction, is between the positive end of one molecule and the negative of the other. These are weaker because they're temporary, because then in just a second they might switch over and they're going to break that IMF because all of a sudden they're going to make it so their electrons are more over here. Dipole-dipole is different now than dispersion forces because this is for polar molecules. So this is molecules that have a permanent dipole. Like for HCl here, the chlorine is always partially negative because it's got a higher electronegativity than the hydrogen. So it's similar but different because it doesn't change. It's always negative on that end. So then a nearby molecule, the positive end is going to be attracted. So that's your intermolecular force. And then you can see over here, all of these are showing the way that these molecules are attracted to one another. So this is stronger than dispersion forces. And then we have hydrogen bonds, which are the strongest of all 3. This is really the same thing as a dipole-dipole, but it's an extreme difference in electronegativities that happens when you have hydrogen bonded with nitrogen, oxygen, or fluorine. I call that NOF because these are the most electronegative elements on the periodic table. 4.0, 3.5, and 3.0. They're really high, and then hydrogen is only 2.1. So there's a very large difference between them, which just creates an even more partial negative and more stronger partial positive. So then the attraction is stronger. So in order to boil something, or you have to break, in this diagram, there's this is like a polar molecule with these IMFs. And in order to boil, you have to break those. So the easier they are to break, the lower the boiling point. The harder they are to break, the higher the boiling point. And that's similar to melting. In melting, you break some of them, not all of them. And then also evaporation is similar. So the easier something boils, melts, or evaporates means that they have weaker IMFs. And if it's harder to evaporate, melt, or boil, then they have stronger IMFs. Also, the solubility, if you remember our lab and how we couldn't really decide whether covalent compounds were soluble or not, the ones that are soluble because they're polar. So they're like water, because water is polar. So water has a partial negative and partial positive charges. So though it's attracted to the ions when you're talking about an ionic compound, but also attracted to, this is representing just a polar molecule, which would have a positive and a negative end. So the covalent compounds are soluble in water if they're polar. Otherwise, nonpolar covalents are not soluble in water. So we need to be able to just look at a molecule now and determine what kind of IMF they have. So if we're going to call LDF is also a different way of saying dispersion forces. So every molecule has dispersion forces. So the questions that you would ask yourself is the molecule polar? If you say no, then it only has dispersion forces. If you say yes, it has dispersion forces, but it has also either hydrogen bond or dipole-dipole, which are stronger. So if it has hydrogen with nitrogen, oxygen, or fluorine, then it's a H bond or hydrogen bond, which, remember, it's not really a bond, it's an attraction between molecules, an IMF, but we call it a hydrogen bond. And then it's not, but it's still a polar molecule, then it's going to have dipole-dipole forces. So if we look at this worksheet, for example, we can do a couple, like here, remember that's trig pyramid, so we know it's polar, and it's polar, so then we ask ourselves, does it have hydrogen bonded to NO or F? It does. So this is a hydrogen bond would be its strongest intermolecular force. Let's do this one here. It's a tetrahedron, and they're not all the same going around. So this is a polar molecule. I'll erase that so you can see. And then we ask ourselves, does it have hydrogen bonded to nitrogen, oxygen, or fluorine? No. So this is dipole-dipole. Here, this one is nonpolar molecule because the fluorine around the boron, they're all the same. So they cancel out. So then this would only have dispersion forces. So then we can also look at boiling point. If we look at, for example, chlorine here compared to bromine, let me make these a little bit easier to read. The bromine is significantly higher boiling point. They're both nonpolar molecules. And the reason that bromine has a higher boiling point means it's got stronger IMFs. They both only have dispersion forces, but the bromine has stronger dispersion forces because it's bigger. It has a larger amount of electrons, so that when they move temporarily to one side or the other, they're going to have a greater partial negative temporary dipole. Dipole-dipole, if you compare like chlorine, which is nonpolar, so it only has dispersion forces, to this one, which is polar. It's a huge difference again in boiling. So this is going to have dipole-dipole, which is much stronger than the dispersion forces. That's why the boiling point is much higher for the one that has the polar molecule that has dipole-dipole. Lastly, we can compare water, which is a boiling point of 100, to the H2S. So they're really similar. They're both bent shapes. They're both polar, but we know that we have a hydrogen bond in the water versus only dipole-dipole here. So because that hydrogen bonding is so much stronger, there's a huge difference in the boiling point because it's much harder to break those IMFs.